As we begin our first chapter here in Calc 2, it's important to kind of lay the groundwork for what exactly our objective is as a whole for this chapter. Now, at the end of Calc 1, you had learned a lot about how to integrate a variety of different functions. And what we're going to be taking a look at here in this chapter is how we can begin to apply the ideas of what an integral is to be able to calculate more than just area under a curve, which of course was the goal of integration in Calc 1. Now, in order to be able to understand these extensions of integration, it'll be important for us to begin here with a quick review of how did we think about integration in Calc 1. So here's at least our quick review to start. Let's suppose that A is an area of a region that lies above the x-axis but under the graph of f of x equals x squared, specifically between x equals 0 and x equals 2. So if I was to go ahead and attempt to try to graph this out, let's suppose that I have a picture that looks something like this. If I was to draw out my curve of x squared, let's suppose that it goes like this, and then also over here. So this is my f of x function. Now, if I'm going from 0 over to 2, and this is the area under the curve that I'm interested in, would be all, the area that I'm interested in is this space over here. Well, I want to go ahead and estimate that using a right Riemann sum with 4 rectangles. Again, this is not a Calc 2 question, but rather this is a question that you would have tackled last semester in a Calc 1 class. So let's take a look at how, though, we would do this, because it's really important to be able to understand this again so we can understand the further applications of integration. So you might recall that if I wanted to find 4 rectangles, cram them into this space, and find their areas to approximate the total, I would need a couple different things. I would need to first be able to establish the width of our given rectangles. And the width of our rectangles we often gave by a symbol delta x. And it was pretty easy to calculate how wide each rectangle would be because we often thought about them as being equally wide. So here, if I have 4 rectangles and I have to cram them into a space of length 2, notice that I can say that since I have a space of length 2 and I want to slide 4 rectangles in there, that means each rectangle can be a half wide. So if I was to go over here and mark out where 1 is, mark out where a half is, and mark out where 3 halves is, I can see each of the bottom edges of my rectangles is starting to be formed. Right, I got a rectangle that's coming over here, in there, and finally over here at the edge. So I got these blue bases. And now I just need to figure out how tall to make them. Well, remember that if I'm doing a right Riemann sum, what that's going to mean is I'm going to start at the right edge of each rectangle and go up until I hit the function, and then kind of just cap off my little rectangle. I'm going to do the same thing for each of these. I'm going to start on the right-hand side, go up, hit the function, and kind of just cap that off. And so I'll do that here for each one of these. And I can see that these blue rectangles don't actually give me the precise area under the region. It appears that they're overestimating. They're giving me more area than what I need. But let's find how much area that's going to be. So I'll say A, the total area under the region, is roughly equivalent to, and it's going to be 1/2 times the height of my first rectangle, to get the area of rectangle number 1. Notice I'm just trying to add up all the areas, and so I start with the first area. My first width is a half, and my first height, notice, is determined by plugging 1/2 into the function. So I would do 1/2 times f of 1/2, and then 1/2 width for the second rectangle, but I get its height by plugging 1 into the function and going up to that point. So f of 1. And notice that if I continue this pattern down the line for all 4 rectangles, I'm going to end up with the following. Now, of course, I'll notice that each of these has a 1/2 in common, so there's nothing wrong with me factoring out that 1/2 and then evaluating each of these individual f's. Since my function is f of x equals x squared, it's pretty easy to go through and square all these values. Notice that if I square a 1/2, I get a 0.25, I get a quarter. Squaring 1 gets me 1. Squaring 1.5 there would get me 2.25. And squaring 2 is going to get me 4. So let's see, I'm going to have a half here, ultimately multiplied by, let's see, if I add everything up here on the inside, I think I get 7.5. And if I was to take 7.5 and cut it in half, I get 3.5. 3.75. So we would estimate that the total area underneath the parabola here is about 3.75 square units. But of course we know that this here is an overestimate. We can see that in the picture. So understanding how this sort of estimation process was done in Calc 1 is really, really important because it helps us again understand the definition of a definite integral. Remember that we had this definition of a definite integral back in Calc 1. We said that as long as the function I was integrating was continuous on the interval from a to b, then the definite integral of a function from a to b, like the integral of x squared from 0 to 2, would be given by this set of symbols. We're very familiar with that. But we really need to understand this set of symbols at the side, because this integral notation was equivalent to what we have here. And while this side can look a little bit confusing and intimidating at times, it's actually really simple to break down. We can already see here right from the start that we have our symbol of delta x, which we had set up above, stands for the width of a rectangle. We also have here this f of xi star, which kind of represents like our different f values that we have over here. Like we have f of a special x, f of another special x, so on and so forth. And so this f of xi star, that represents the height of a given rectangle. And so what we're doing here is we're taking that height and that width and we're multiplying them together and we're getting an area. Then of course we have a sum. We have a summation here that says add up all those areas. And this little counter variable of I just stands for which rectangle I'm currently working with. So this says find the area for rectangle number 1 and add it to the area of rectangle number 2, and then add that to the area of rectangle number 3 until you hit rectangle number n, until you run out of rectangles. So my summation here says that I'm going to add up the areas of n rectangles. That's the goal. And then, of course, if we were to try to find the area by using this definite integral, in Calc 1, we slapped a limit on this thing. And we said, how about the number of rectangles that I'm going to use isn't just going to be 4 or 5 or 100, but what if I let that number of rectangles go off to infinity? So here I'll say, let the number of rectangles go to infinity. Now, we're going to see this notation over here show up very, very frequently throughout this entire first chapter. In fact, we'll see it in pretty much every single section. And our goal is going to be to try to understand how we can take this notation and rework it slightly. So instead of, again, just measuring areas under curves, we can measure a variety of different things with the same integration process. Now, in the next videos, we'll take a look at our first extension of this. That is, specifically, how do we use this idea to try to find areas between two different curves?